Hello and welcome back. In the previous few videos, we were discussing kinematics, which is the relationship between the position, velocity, and acceleration of an object. We didn't really talk about what causes objects to accelerate in the first place. So that's what we'll discuss in this law when we look at Newton's laws. So Newton's first law, you hear this as an object at rest will remain at rest unless acted on by an outside force. Now that's what happens if the object is at rest. What if the object is in motion? Well, Newton's first law also tells us that. If an object is in motion, it will continue to move at a constant velocity unless acted on by a net force. So remember, velocity is a vector quantity. It has magnitude and direction. So an object that is moving will move at a constant speed and a constant direction unless acted on by an outside force. So if you look in the slide, you'll notice I always say net force, right? Net just means the sum of the forces, okay? So Newton's first law tells us if I sum up all of the forces and it's equal to 0, then an object at rest will remain at rest, or if it's in motion, it'll move with a constant velocity, okay? So if I have two forces that perfectly cancel out, it'll obey Newton's first law. So in the previous slide, I said an object at rest will remain at rest unless acted on by an outside force. Now we know that some objects tend to want to remain at rest a little bit more than other objects, right? Some objects are really, really hard to accelerate. The usual example I give is like something like a shopping cart versus a car, right? If a shopping cart, you push on it a little, it moves pretty easily. Now if you've ever been in the unfortunate situation where a car's broken down, you really have to push on a car very hard to get it to start moving again. And what we would say is we say that a car has a large inertia. So inertia is the tendency for an object that's at rest to continue to stay at rest, or the tendency for an object that's moving to continue to move with a constant velocity. So we would say something like a car has a very large inertia, because a car that's at rest tends to want to stay at rest. And a shopping cart has a very small inertia because a shopping cart that's at rest tends to want to stay at rest. But likewise, once the shopping cart is moving, it's pretty easy to bring it back to rest. Okay, so you can very easily stop a shopping cart. But once a car gets moving, if you've ever pushed a car that's stalled, it's really hard to bring it back to rest, right? You got to kind of hurry up and get in the driver's seat so you can push on the brake and get the car back to rest. Otherwise, it'll just keep rolling. So the way we measure inertia is with mass. So hopefully that makes sense, right? A car has a lot of inertia because it weighs a whole lot. It's got a lot of mass. And the shopping cart has a smaller inertia because it has a smaller mass. So Newton's first law tells us what happens if the net force on an object is equal to 0. So what happens if we have a net force acting on the object and it's not equal to 0? Well, Newton's second law says that the net force acting on the object is equal to mass times acceleration. Notice that this agrees with our concept of inertia, right? If I solve for acceleration, I see the acceleration is the sum of my forces divided by mass. So the larger my inertia, the more massive the object is, the smaller my acceleration, right? So more massive objects are harder to accelerate. Okay? Now, we measure force with units of newtons, and we can use this formula here to see what a newton is equal to. So if we apply dimensional analysis, we have the units of force are equal to units of mass times units of acceleration. Mass, remember, is measured in kilograms. Acceleration is measured in meters per second squared. So what we see is that 1 newton is equal to 1 kilogram meter per second squared. So we've looked at, what happens if the net force is 0, or what happens if the net force is not equal to 0. We haven't really talked about what forces are. And so now I want to go ahead and introduce two forces. The first force I want to introduce is the gravitational force. So we know that objects near the surface of the Earth will accelerate towards the ground with a constant acceleration that's equal to g. So using this, we can already say what the force due to gravity is, right? So if I have an object, it's in free fall. then the only force that acts on the object is the force due to gravity. So according to Newton's law, the sum of my forces is equal to mass times acceleration. And if the only force acting on the object is gravity, then that says the force due to gravity is equal to mass times acceleration. But I know what my acceleration is if the object's in free fall. It's mg. So looking at this equation, I can already see the force due to gravity is equal to mass times g, where g is the acceleration due to gravity near the surface of the Earth. Now technically, this is actually a vector quantity. So the force due to gravity, like I've drawn here, it always points down towards the surface of the Earth, so towards the floor. Now, this is the force due to gravity. Let me just open up a blank sheet here, a white screen. But I mean, if I have a box and it's, say, sitting on the floor, right? So if I've got, here's the floor, I put a box down. I know that there's going to be this force due to gravity that's pulling down on the object. But the object does not fall through the floor, so there must be another force that is exerted on this object that stops a box that's sitting on the floor from falling through the floor. So there must be an equal and opposite force pushing up on the object, right? Because I know that when an object, a box or something, is sitting on the floor, its acceleration is equal to 0. And Newton's law tells me that means the sum of my forces is 0. Okay? So an object sitting on the floor, it doesn't accelerate down, so there must be a force pushing up, and I've already denoted it as F sub n here. This force that prevents objects from falling through the floor or whatever surface they're in contact with is called the normal force. Okay? So it turns out that whenever an object is in contact with a surface, there are two types of forces that arise from this. There's the normal force and the frictional force. Right now I'm just going to focus on the normal force, and in a later video I'll talk a little bit about friction. So the normal force always points perpendicular to the surface of contact, and it perfectly cancels any forces that are pushing perpendicular to a surface. Okay? So what do I mean by this? You might think, well, the normal force pushes up, right? It cancels gravity. And the answer is, well, yes and no. It depends on what you're looking at. So if I have a box that's sitting on a flat surface like this, then yes, I have a force due to gravity that points down and a normal force that points up. And the normal force perfectly cancels the gravitational force. But if we imagine I take a box and I hold it up against a wall, and I apply a force and I push on that object so that I'm pushing it against the wall, well, when that happens, right, the wall is a hard surface. It's not a fluid. I can't push a box through a wall like I could, water. So the wall must be applying a force back on this object. That's why the box doesn't, pass through the wall when you push on a box that's held up against the wall. Okay? So in this case, that force that the wall exerts on a box is the normal force, right? It's a force that's perpendicular to the surface. This is my surface here, okay? This normal force here is perpendicular to that, and it's perfectly canceling the force that is perpendicular to the surface, right? So I'm applying a force that's perpendicular to the surface, and that surface applies an equal and opposite force that cancels the applied force, okay? Now, in these two examples, the normal force and the applied forces were anti-parallel. They kind of pointed along a straight line. But that's not always the case. So here, on this far right, I give an example of a box that's sliding down a ramp. Now here is my hard surface, right? The ramp itself is a hard surface. So the force due to gravity, if I decompose the force due to gravity, it has a component that points perpendicular to the surface, and then a component that points parallel to the surface, right? So there's this component due to gravity that goes something like this. It's going perpendicularly against the surface. So, right, the normal force cancels any forces that are applied perpendicular to the surface, right? This box isn't going to go straight down, because to go straight down it would have to go through the surface of this ramp, and that's impossible. So the normal force applies a force that's perpendicular to the surface of the ramp, right? This normal force is perpendicular to the surface of the ramp, and it perfectly cancels the component of my force due to gravity that's perpendicular to the ramp's surface. Okay, so the normal force, it's not always necessarily going to point straight upwards. It's not always necessarily going to perfectly cancel the other forces, but it'll always perfectly cancel the component of the forces that are perpendicular to the surface. Okay? That's the real important idea. And I think at that point, I'm going to end this video, and in the next video, I'll talk about free body diagrams, which is a way that we can graphically represent what's going on. In fact, I already have a few free body diagrams here in this slide, so you already kind of get the idea. And then we'll actually look at some examples and apply Newton's second law to solve a few basic problems.